Hi, my name is Zvi Avraham, and I'm a founder of a company named Data. And in the data, we're building a marketplace for real-time machine-generated data. And to build such a marketplace, we were looking for common protocol which able to work with dumb-based sensor, with very simple sensors, and at the same time will support smartphones and regular servers. In short, we're looking for a protocol which can talk with any kind of device. And this is how we come to MQTT, which is purpose of our talk. The talk will be technical, but because we will cover too many subjects, we will not have an opportunity to drill down in the details. So MQTT is based on PubSub, which is short of publish subscribe. Publish subscribe is a messaging topology or messaging architecture, which is very common in IT in the internet, but less common in the embedded and Internet of Things and M2M world. And because to understand what is MQTT, what is MQTT, we first need to understand what is PubSub. So PubSub, usually we have three entities: publishers, brokers, and subscribers. Publishers publishing some kind of information, message, or data point to something called topic. And the other entities subscribe to topics and then receive the messages. And like every problem in computer science, have communication between publishers and subscribers resolved by using something else, indirection. Broker, it's somebody in between, which is intermediate between publishers and subscribers. Problem is much more complex when we have many subscribers, like millions of subscribers, subscribing to different topics. And when we have many publishers, thousands to millions of publishers. And in Internet of Things, we're talking about billions of devices, even trillions of devices. One of the advantages of PubSub, it's a broadcast. Usual messaging topologies, like point-to-point messaging, usually send message from one client to another. And if we need to broadcast message to many clients, we need to duplicate, to copy this message many times. And this vast is bandwidth. So in PubSub, we have something called one-to-many messaging, or fan-out. So we can send message once, and the broker or something else will duplicate this message to many clients, to many subscribers. So now, after introduction, what is PubSub, we'll talk about actual MQTT. And again, I was developing PubSub systems, proprietary PubSub systems for Comet and WebSocket and many other protocols. And I had the feeling that I reinventing the wheel. All those features I needed with time, I think I reinvented the wheel because there had to be something standard for PubSub. And this is how I came to MQTT, which is short for Message Queuing Telemetry Transport. And telemetry is a non-sexy word for Internet of Things and M2M, connected devices, and all the other buzzwords. So let's talk a little bit about the history of MQTT. MQTT was invented by IBM in 1999. In 2008, IBM released complementary spec called MQTT-S, which is MQTT for sensor networks. In 2011, IBM and Eurotech donated MQTT spec and MQTT reference implementation to Eclipse Foundation and formed Eclipse M2M work group. And just recently, in March 2013, they formed OASIS MQTT technical committee, which is working on standardization of MQTT protocol. So I think everybody knows this saying. The nice thing about standards that you have so many to choose from, by Andrew Tannenbaum in his book Computer Networks. And we indeed have a lot of standards to choose from, and standards and specs. So for example, we have in MQTT world, we have two major specs, MQTT version 3.1 and MQTT-S version 1.2. But the most important for me thing about these specs, that they are very, very lightweight. MQTT is only 42 pages long, and MQTT-S spec is only 28 pages long. Combined, there are only 70 pages. The protocol, alternative protocol similar to MQTT-S called CoAP. CoAP is short for Constraint Application Protocol, which is also a protocol for sensors. And CoAP itself, the only CoAP is 88 pages long. And all the telecom standards, by telecom standards bodies like ETSI, M2M, Technical Committee, some number, use CoAP as their low-level REST interface for devices and sensors. But all the other layers of telecom standards and specs are huge, in hundreds, maybe thousands of pages. So for small companies and startups, hobbyists, hackers, makers, etc., it's impossible to implement 100-page spec. So we had to go to lightweight specs like MQTT. So what's MQTT? MQTT is message queuing telemetry transport. Essentially, it's a lightweight publish-subscribe protocol standard for traditional networks. Traditional means IP networks. It's data-centric. It separates data payload from metadata, which is topic name. So MQTT topics are very similar to file system paths. So in this example, we have WSN / sensor name, in this case is R1, / temperature or / pressure, or another sensor R2 with temperature and pressure. So what essentially MQTT does, in MQTT, unlike other sensor protocols, you don't need to know IP address or serial number or MAC address of the device you're talking with. You just need, you decouple publishers and subscribers with topics. And like in file systems, we can use wildcards. Plus means single level wildcard, and this character means all the paths after this level. Sorry for the loaded slide, but the purpose of this slide to show that entire MQTT spec can be fit into single slide. We have only 14 commands, and this is the reason they can be fit into 4-bit. MQTT, unlike all the modern web frameworks, etc., it's not text-based, it's binary-based, and it's very efficient for parsing with Erlang bit syntax, for example, because it's binary-based. So we have 14 commands, which can be encoded with 4-bit code. And we have connect command, which I didn't say it, but MQTT itself based on TCP. So we still need TCP sockets. But once we connect it via TCP socket, we need to send connect packet, and then to the broker from the device. And the broker acknowledge with CONAC. If the client want to publish the message, client sends the publish packet, and the broker acknowledges with pub-ack. There are many other pub-rec, pub-rel, and pub-comp. This is for implementing higher quality of service, which we'll be talking later. And if the client wants to subscribe to specific topic, it sends subscribe message, and the broker answer with sub-ack. Likewise, for unsubscribe message, unsub-ack. And because it's based on TCP communication, we need to send periodical pings. So the client sends ping rec, and the broker replies with ping response. And in the end, if we want to disconnect, we send disconnect message. But what if we need to send disconnect message, and IBM, when they designed the spec, they used the trick because the opcode of the message has double meaning depending if it's come from the client to broker or from the broker to client. So if publish comes from the client to broker, it means that clients want to publish the message to the topic. But if publish comes from the broker to client, it means that client received the message from somebody else. MQTT has something called last will and testament. And as I said, normally if MQTT client wants to disconnect, it sends explicit disconnect packet. But what happened if we had interruption, the TCP socket is closed unexpectedly? So when client sends connect packet, he may set up a will, a last testament. So if I'll die, the connection will die unexpectedly without sending disconnect message, then publish this message to this will message to will topic. This is a trick, this trick can be used for implementing presence and monitoring of devices, and it's very similar to Erlang trap exit mechanism in Erlang and links and signaling in Erlang. As I said, MQTT is essentially a framing protocol above TCP, but the only thing, but one of the important things is quality of service levels. So standard MQTT has 3 levels, 3 quality of service levels. QoC 0 means best effort and no guarantees. So message will be delivered at most once. And MQTT has quality of service 1, which means message will be delivered at least once. So delivery is guaranteed, but the duplicates are possible. And the most strict level is a quality of service 2, means message will be delivered only exactly once. So it's guaranteed delivery without duplicates. Another important, interesting thing in MQTT that they kept reinventing in proprietary protocols called clean session flag. So when MQTT broker sends connect packet, he has a flag named clean session. If clean session equal to 1, it's essentially like every reconnect is a new session. So broker will forget all the subscription and all the session settings on each connect and disconnect. But if we want to reconnect and let broker to remember all the settings and subscription, we need to use clean session equal to 0. Another interesting property of MQTT is retain flag. So when message is published, there is something called retain flag. With messages published with retain flag set to 1, MQTT broker will remember the last message. This is very useful for systems with low update frequency. So if we have some message with updated, some measurement which updated only once per hour, so new client will get update, may wait 30 minutes to hour to new value. So with retain flag, it doesn't need to wait. And this is less standard, not standard yet, but there is possibility to use MQTT over WebSocket. So we can open MQTT connections from any web browser, even web browser without WebSocket connection using fallbacks. It's essentially a JavaScript API, and it supports binary data. There's a small company called Facebook, and they also use MQTT for their mobile applications. If there's only one MQTT proper book by IBM, it's called IBM MQTT Redbook. It's ebook and can be freely downloaded. And there's another book which has only one chapter about MQTT. So now when we have some understanding about MQTT, let's talk about MQTT-S, which is MQTT sister spec for sensor networks. So there's a TCP joke on Twitter, and there's a corresponding UDP joke. Yeah. Why talking about this? Because the difference between MQTT and MQTT-S is essentially the same as between TCP and UDP. MQTT requires reliable point-to-point auto-segmenting streaming connections, while MQTT-S only requires unreliable datagrams. So in case MQTT designed for traditional IP networks, and it requires TCP IP, but MQTT-S can work on any non-IP transport and on UDP using datagrams. So in case of MQTT, traditional networks means Ethernet, Wi-Fi, 3G, etc. And MQTT-S can work on short-range RF, long-range RF, any RF which has point-to-point or mesh networking. The minimal message size in MQTT is 2 bytes. It's only ping. The real messages will be much larger, especially because topic name is a textual string, and it can be very long, quite large. But MQTT designed to work on protocols like Zigbee and Bluetooth, which has very short packages, like 128 bytes and even less. Other differences is that MQTT is designed to work on battery-operated devices or devices which can have sleep mode. And even in MQTT we have something called dump client or simple client, or QoS, quality of service -1, which means very dump client, which has can send only several bytes, and that's all. When we work with MQTT, because of TCP, we need to know host name or IP address and ports for MQTT endpoint on the broker. But MQTT-S designed for embedded devices and sensors, and we can't go to million devices and configure each one with IP address or host name. So MQTT-S from the beginning has something called gateway auto-discovery, and even support for multiple gateways, where some gateways are primary and another gateways are in fallback mode. So let's talk about MQTT-S. MQTT-S designed to be very similar to MQTT. It essentially reuses MQTT spec. This is why MQTT-S spec is only 28 pages long. And it has exactly the same semantics for PubSub as MQTT. MQTT-S clients are wireless sensor network nodes, and they communicate to MQTT-S gateway, which forwards the messages to MQTT broker on IP networks and vice versa. The gateway just translates messages between one wire format, which is MQTT-S format, and MQTT format. So normal MQTT broker will understand the messages. And the most important for me thing is that MQTT-S designed to work on any sensor network architecture or transport. As I said, MQTT-S adds another quality of service called simple client profile. And in this best effort, so no guarantees. It's similar to MQTT-QS quality of service level 0, but he works with, it doesn't require connection setup, and it's only transmit only. So this is a diagram which shows two networks, sensor networks and traditional IP networks, and two sensor actuator clients, which has MQTT-S clients software. And in between sensor network and IP network, let's call this Zigbee. This is Zigbee network, and this is Ethernet network. Usually we have MQTT-S gateway, which translate messages from one format to another and vice versa. And on traditional network, we have MQTT clients which talk directly to the broker via TCP sockets. So before we drill down to wireless sensor networks, we need some intro to Zigbee. So Zigbee is a mesh communication protocol for wireless sensor networks managed by Zigbee Alliance. And there are many different vertical profiles for Zigbee, even for remote TV control and smart energy, smart metering, etc. But for our purpose, all we need to know is that there are three types of Zigbee devices, at least one coordinator, one or more routers, and one or more end devices. And the difference between router and end device, that end device can only receive or send messages, receive or transmit messages, but routers can retransmit for another end device or another router. And we must have coordinator, or in this diagram it's called base station radio on the networks, and coordinator must be connected to power source, because if coordinators goes down, the network goes down. And usually all these modems are exactly the same. The role is, if it's coordinator, router, or end user, it's just a firmware. So Zigbee, how do we program Zigbee? Zigbee has 3 modes: direct mode, AT modem mode, and API mode. For our purpose, most interesting is API mode, because it can simulate AT modem mode. And AT modem mode used for getting and setting registers or getting device info, like for example, Zigbee serial number or many other properties. And in API mode, we can send and receive Zigbee frames and also AT commands. So if somebody wants to new to wireless sensor networks, the most straightforward and simple way is to buy a book called Wireless Sensor Networks and corresponding kit, which costs $115 or something. And this is the most simple way to start with building sensor networks. If somebody was, usually Zigbee radio need to be connected to some kind of microcontroller. And there are modes when Zigbee radio can work independently, but for most interesting cases is when Zigbee is connected to a microcontroller. And we used Arduino. Arduino is a small microcontroller which has a follower, many makers and hackers and physical computing using Arduino for their project. Arduino comes in various shapes with extension boards called shields for thousands of extension shields. This is a comparison table between Arduino and small Linux machines like RaspberryPi and BeagleBoard. They cost the same, but they're different things, because if somebody wants to directly control hardware devices, Arduino is better. But if somebody needs Linux machine, it's better to take a Raspberry Pi or BeagleBoard or any other device. And we program Arduino with C++ based language called wiring. I will not go into this example, but essentially it's a two function setup and loop. And in setup we say that pin number 13 will be used for output, and in the loop we emulate the blinking LED. So from now we'll talk about, it's like case studies of implementing of Zigbee gate, MQTT-S over Zigbee gateway for M2M and Internet of Things. As I said, we may have multiple wireless sensor networks. Each one, by the way, can use different technology like Zigbee or Bluetooth. This one can be Zigbee and this can be Bluetooth. But on the edges of the networks we have to have a gateway, which essentially acts like proxy between two networks. And in yellow, it's a traditional IP network where a broker is located. So sensor on Zigbee networks can communicate with another device on Bluetooth network via the broker, because the underlying protocol is MQTT-S. This project was implemented by two students from Ben-Gurion University under my supervision and Professor Yuda Ben-Shimon. So let's talk about this project. Wireless sensor network node was implemented as Arduino XBee modem. XBee is essentially Zigbee, but because of trademarks and trademarks issues, it's called XBee and not Zigbee. And this is the XBee modem. This is Arduino, and this is a battery. This is essentially a battery-operated device. And here we see network, wireless sensor network with 3 nodes and a gateway running on the laptop. And this is the coordinator, and each one has end user Zigbee. As I said, because our MQTT-S gateway implemented in Erlang, and it's very easy to port Erlang to small embedded ARM Linux machines such as Raspberry Pi, even easier than porting C code, because I had to port C code, and it took me more efforts to port C code than to port Erlang code, even that Erlang code uses CNIF-based library inside. It just rebar, compile, and it works. And another ARM-based device from Texas Instruments called BeagleBoard. And via serial, we have XBee modem, XBee coordinator, communicated via USB to serial protocol. There's something called Nike Plus, which is the sensor which goes to the Nike shoes. And this is an example for dump client, or QS-1 profile. And here we have added to our wireless sensor network node, somebody reverse engineered RF protocol used by Nike Plus. Nike Plus uses Apple proprietary Apple accessory devices protocol, and somebody reverse engineered it and sent the kit. So we connected this device to this, and from here it just uses MQTT-S over Zigbee. And this Nike Plus sensor, every send measurements like how many steps I did, how many miles I ran, and stuff like this. And most important, unique ID. So many people implementing like Foursquare check-in, automatic Foursquare check-in, or opening doors just automatically because you proximity with Nike shoes. So why did we use Erlang in this implementation of this project? So Erlang is, as we saw, Erlang ideal platform. I think is most ideal platform for implementing large-scale publish-subscribe systems. Large scale means C1, 1 million to 10 million concurrent clients. It's ideal for implementation of gateways and proxies, network gateways and proxies. We use Erlang bit syntax and binary comprehensions to parse Zigbee, MQTT, MQTT-S packets. And it's very easy to port ARM-based to Erlang code or Erlang releases to ARM-based embedded Linux systems. Not only RaspberryPi and BeagleBoard, but also for professional ARM-based single-board computers. So this is the example of MQTT fixed header, and Erlang code needed to parse it. So bit syntax. Enough said. So MQTT broker design is very based on Cowboy. We have one Cowboy process per MQTT or WebSocket client. It receives, sends, and handles MQTT protocol frames using bit syntax. We have one GAN server for MQTT subscriber, and one GAN server for each, one GAN server plus one edge table per topic. So MQTT subscriber GAN server manages an MQTT client session. It may survive TCP socket disconnect. It depends on quality of service we work with. And if we work with higher quality of service, it will queue messages between disconnects. It depends on clean session, flag, and quality of service. And each topic is a GAN server which manages the list of subscribers per topic in edge table. And its most important job is to broadcast messages to all interested subscribers. And we have a subscriber manager GAN server, which manages list of subscribers, creates new subscribers, removes subscribers, and handling one-to-one messaging. MQTT protocol itself doesn't have notion of point-to-point messaging, but our proprietary extension, and it's going to be standardized. There's a topics manager GAN server, which manages the heavy table of all topics, and it handles publishing to the topic. So broadcast this message to all topic subscribers. Let's talk about scaling the networking stack. This is mostly applied to the broker side, because for now, Zigbee networks are limited to 64 nodes or something, and Bluetooth networks limited to 7 or 11 devices. Okay. So tuning networking. First of all, we need to tune Linux TCP stack. There are lots of guides on in the internet how to tune your TCP stack depending if it's 1 gigabit or 10 gigabit, etc. One of the important things is SynFlood or SynCookies. It's essentially accumulation of half-open sockets, and being behind load balancer solves this. So I recommend being behind load balancer. Broadcasting throughput problem. Let's say we have millions of concurrent clients, and we need to send periodic pings. This applies to MQTT. So we will recognize sooner or later that the socket is disconnected. And just sending these pings alone to millions of clients requires a lot of bandwidth. And this is a problem. And the only problem is to switch to something else, or to make sure that these pings are very small, like 1 or 2 bytes. Standard MQTT listens on port number 1883, and MQTT over SSL, the standard port, YANA port number is 8883. And if somebody works with MQTT over SSL, it's better to do SSL termination on load balancer, because if you do SSL termination in the broker itself, each connection will take a lot of memory and CPU, like 1 order of memory more. And of course, poor man quality of service always separate ports for different protocols. and between control and data flow too. So scaling on the Erlang side. Erlang is the platform from large-scale systems and scalable, highly available systems, but the rest, out of the box, you still need to use few tricks to make it scale. First, we're sending messages between processes always as a binary. Especially this is relevant for broadcast. If you have one process sending message to a million processes, better to send it as a binary, otherwise it will take much more time and CPU. We're broadcasting messages at low priority. We actually decrease broadcasting process priority. And the reason is to not interfere with accepting new MQTT clients. We also wrote our own broadcast timer code, since built-in timers do not scale to large number of processes. And because we use GAN server for each new subscriber and each new topic, we worked with few tricks to implement fast spawning on new GAN servers. One of the first things I learned when working with Erlang is to always implement data flow, not to use Erlang built-in distribution for data flow. Erlang data flow has better use cases for control flow management, cluster management, but for data flow, as they all use TCP sockets, or in our case, we just use 0MQ. We use a lot of Erlang open source libraries, but I'll mention a few. Cowboy is essentially high-performance embedded web server. We started with Mocky-Web a long time ago. Then we had to switch and evaluated Missultine and Cowboy when Cowboy was just a few months old. And we decided on Cowboy after the benchmarking. And I recommend using Cowboy as an engine for your networking code. Not only WebSocket or HTTP, because Cowboy has built-in branch TCP socket acceptor, so it can be used to implement any network server. For communication with the serial port, like Zigbee coordinator, we use Tony Rockwell's SL library. For pretty printing binary dumps, we use BinPP. For logging, Basho Lager. And for 0MQ, L0MQ2, I think by Yuri Rashkovsky. And many, many others. I will need the entire presentation to mention all the code we use. I moved the demo. I had to show, originally I planned to show the demo, but because for some logistics, the demo, I will be doing demo at Lightning Talks after 8. And that's it if somebody has questions.
We have about 5 minutes for questions, so if you have any for Zvi. So the question is, how long does it take to complete the project?
If somebody took a software engineering course, they always say that initial version takes only 5% of time and resources and budget. So initial version of MQTT broker was written very quickly, but when all the maintenance take a lot more times than the question itself. If we're talking about MQTT-S gateway itself, it was it's two-semester project by 2 students. And as you know, students, they always leave things to the end. And actually, for example, first semester students, the students already learned plain Erlang, not OTP. So first semester, I prepared the learning plan. They had to learn OTP, GAN FSMs, all the stuff they didn't learn on the university course. And they had to learn Arduinos and Zigbee. So all these preparations took much more time than the actual project. So because it's interdisciplinary project with many moving parts, it took 2 semesters, part-time. So students had to work 2 days per week on the project, not excluding exam time.
I have somehow unrelated question, sorry. You have mentioned that your proprietary extensions will be in the protocol, right? So is your corporation somehow protocol defining, or have a large political, per se, weight in the MQTT community? I'm sorry if I missed it.
Just a second. So MQTT, for now, MQTT standardization is led by an organization called Oasis, and they have a technical committee inside Oasis, which is responsible. Before that, it was all led by IBM. So you go to mailing list and you say, I need one-to-one messaging, and this is my proposal to do one-to-one messaging. And after next release of IBM Broker has this functionality, but it's not part of the spec yet. Now with Oasis, and actually it's very cheap and to be member of Oasis. We're not yet member of Oasis, but we have plans to join Oasis MQTT Technical Committee. And what I want to say, MQTT spec is very lightweight. This is good and bad. Comparing to XMPP, which is a huge spec with many extensions, this is good. But it's also bad because you miss a lot of functionality. And you need to convince all the other people that 40 pages spec is good. But the huge chance that you will need something and it's not there.
Do we have any other questions? I have one question. Do you have any thoughts on the utility of MQTT-S on self-organizing networks? So it seems like you have single points of failures where the sensors have to talk to routers or gateways. Do you have any thoughts on whether MQTT-S could be used in a scenario where where the sensors themselves are self-routing or self-routing the messages?
There's something called MQTT-S forwarder, which actually is forward messages between from end device, wireless sensor network node to MQTT-S gateway. And in the protocol, they have special frame message for forwarding. But I don't know if it's related to your question. It's possible, but I don't know about the status of this and if somebody works on it. But in theory, it's possible.
Okay, great. I think that is all the time we have right now. Please remember that we will have lightning talks and we'll be able to see the demo. I think we're breaking for lunch, and then we'll reconvene after lunch here, or if you want some other lesser important tracks, you can go to those too. Maybe Hoff's.